We're going to continue on here in the acid base chapter. So last time we got into more about acids and bases. We talked about a lot of calculations that you could do. We talked about the pH scale. And remember, pH scale goes from 0 to 7 to 14. And again, below 7 is acidic. Above 7 there is basic. And really 7 there on the nose is neutral. As we talked about, as you go from 7 sort of towards 0, you do become more acidic. And as you go from 7 kind of towards 14, you become more basic. And we have several sort of calculations involved here. We talked about Kw, which is concentration of H plus times concentration of OH minus, and that does equal 1 times 10 to the minus 14. We could use Kw in calculating those concentrations to help us decide if a solution is acidic, basic, or neutral. It's really the same calculation. And again, if your H plus concentration is larger than your OH minus, then it would be acidic. If your H plus concentration is less than your OH minus, it would be basic. And if your H plus concentration equals your OH minus concentration, and by the way, that would be 1 times 10 to the minus 7, which is why neutral really is a pH of 7, you would end up with a neutral solution. We talked about calculating the pH, which is minus the log of the H plus concentration. We talked about a similar scale that measures the OH minus concentration, and that is the POH, which is minus the log of the OH minus. And really the helpfulness of those two values is if you take the pH plus the POH, that will equal 14. So it does give you some variation or variety in terms of how you might go about solving a problem. We also talked about that if you have the pH value, you can get the H plus concentration from it. And that is the inverse log of the negative pH. And as we talked about on most people's calculators, that usually will pop up a 10 and a caret when you do punch that in. Same thing with the POH. From it, you can get the OH minus concentration. And it's really the same calculation as well. That's the inverse log of the minus POH. And once again, that will put like a 10 and a caret minus POH here. We talked about the idea that it should only be one answer, right? When you're asked, is it acidic, basic, or neutral? And probably you should always look at the pH value, since again, that is really the scale that most people have in their head. And again, not it's acidic, basic, and neutral at the same time. We also talked about the idea of sort of strong acids and bases. Also some weak acids and weak bases. And remember that the relationship that happens between an acid and its conjugate base or a base and its conjugate acid is if something is strong, its conjugate partner on the other side of the arrow will be weak. And if it's a weak acid or a weak base, its conjugate partner on the other side is considered to be relatively strong. Again, not like a strong acid or base, but will continue, as we'll talk about in this chapter, to continue to sort of react. There's sort of a list of some strong acids that we talked about. Strong acids 100% dissociate in solutions. So does strong bases. You have your nitric acid. You have your hydrochloric acid, you got your perchloric acid, your hydrobromic acid, your hydroiodic acid, your sulfuric acid. So this is a nice list of some strong acids. A lot of strong bases will have hydroxide in the actual formula. So things like sodium hydroxide, potassium hydroxide. You kind of hang over to the right there, a little calcium hydroxide, barium hydroxide. So these are some strong bases, again, from group 1 and 2 on the periodic table that have hydroxide in the formula. And as we talked about, that's really where the name sort of comes from. Alkaline means basic, so that's where we see a lot of our strong bases come from. Places like the alkaline metals, alkaline earth metals is where a lot of those guys do come. In terms of weak acids or weak bases, they do not really fully dissociate in solution. They actually mainly stay together, weak acids or weak bases. They are considered weak electrolytes, which is pretty much what that definition is, but they will still break apart a little bit. And because they do break apart a little bit, they're able to, in the case of a weak acid, still produce some H plus in solution, which is why it's still considered an acid. And in the case of a weak base, it's still able to produce some OH minus in solution. And that is what makes that also a weak base, or still a base. And those weak acids and weak bases typically will have the sort of reversible arrows sort of associated with it when you do write the equation for those guys. Any questions on any of those things we talked about, I think, last time? Okay, then I think we left off on these two examples here. So we're looking for what is the pH of a 2 times 10 to the minus 3 molar nitric acid solution, and what is the pH of a 1.8 times 10 to the minus 2 molar barium hydroxide solution. So why don't you take a couple of minutes. Those should be recognizable to you as a strong acid and a strong base. Yeah, so see what you come up with. Okay, let's take a look here, see how you're doing. So first off, hopefully we can recognize this as a strong acid, which is nitric acid. That means that when it's really in solution, it is going to 100% break apart into H plus and nitrate here. Now, in terms of the pH, which is minus the log there of the H plus concentration, actually, this then would be the most important guy to figure out its concentration. So since we do know that this is 2 times 10 to the minus 3 molar, the concentration of H plus in this case would also be the exact same number, right? And that is because it is a 1-to-1 relationship between those two. So if you remember how concentration works, if it's a 1-to-1 relationship between the whole thing and an ion, it's the same. If it's like a 1-to-2 relationship, like it breaks apart into a couple of ions, then you need to multiply the concentration by 2. Just to remind everybody, just in case you're not sure what I'm talking about, yes, that is 2 times 10 to the minus 3 moles per liter of nitric acid. You do a little stoichiometry. 1 mole of nitric acid gives you 1 mole of H plus. Those cancel. And now you end up with 2 times 10 to the minus 3 moles per liter of the H plus. That is the long version of what I just said to do, by the way. Yes. Any questions on that there? All right. So since we really do know the H plus concentration, we can put it in. The pH is equal to minus the log of 2 times 10 to the minus 3. Remember, as we talked about the other day as well, depending on your type of calculator, if you have a display calculator, you're going to put that in exactly the way it's written. Negative, not to subtract button, 2 with the exponent button, and a -3. If you do not have a display calculator, you need to start with the number, then hit log, and then hit the negative button. Whichever way you're rolling with that, you're going to end up with a pH of 2.7, I hope. Yes. Any questions on that there? Why is the pH 2.7 in terms of sig figs and all that good stuff? The concentration has 1 significant figure, which means the pH gets 1 decimal place. So again, remember that The number of significant figures in the concentration is actually how many decimal places you should take a pH or POH value to. And then obviously if you're going backwards, like you could do as well. If you have one decimal place, you should have one sig fig. Any questions on the top one there? Looking at the bottom one, which is a strong base, that's a little barium hydroxide. And our barium hydroxide here is going to also 100% break apart into a barium ion and a couple of hydroxide ions. In this particular case, we do not have the H plus concentration, but we do have the OH minus concentration, which means it would probably make sense to first calculate the POH, right? Not the pH. We do need to get the correct concentration for the OH minus. So since this is 1.8 times 10 to the minus 2 molar, what would be the hydroxide concentration? I need to take 2 times 1.8 times 10 to the minus 2 molar to have the correct concentration of hydroxide in that solution, because it is a 1-to-2 relationship in terms of how it breaks apart. That gives us 0.036 molar as our hydroxide concentration. That then would be a POH minus the log 0.036. And that gets you a 1.44. Once again here, if you thought by some chance that that was the pH, it should not make sense to you because this is a base, right? So we should at least have a basic pH. So we could then use our pH plus the POH equals 14, which means in this case, the pH would equal 14 minus the POH of 1.44. And that's going to get us 14 minus 1.44, a 1256, which does make sense since that is definitely basic. And this is a base. Yes. Any questions on any part of that there? And again, to show you the long version here, this would be 1.8 times 10 to the minus 2 moles per liter of barium hydroxide. Using the stoichiometry, there is 1 mole of barium hydroxide to 2 moles of OH minus. Those cancel, and that is essentially why we are multiplying by 2. That's basically, again, where the 2 comes from now. That gets you obviously there. Any questions on either of these? So sometimes you will come across a problem where they will not just give you sort of a generic H plus or OH minus concentration. They may lay up an actual formula of a strong acid or strong base. And obviously you want to make sure you either get the correct H plus or OH minus concentration when you're going to calculate it. The good news is most of the strong acids are monoprotic, which means it's kind of for the acid, almost in most cases, a 1-to-1 relationship. Really, it's the bases and group 2 guys in terms of bases is where you probably have to run into adjusting the OH minus concentration. Any questions on any of that there? Okay, then here is a table. You should have a similar one in your book, but this is a table of some of the strong acids that we talked about. And again, our strong bases, which pretty much is like group 1, go right and down into group 2 is where you find kind of all your strong bases that happen. So let's talk about what happens with weak acids and how we deal with those. And it is a little bit different. Now, when we're dealing with a weak acid, you could again write the sort of dissociation of that weak acid 1 of 2 ways, as we've been talking about. You could use water, which you get the H3O plus, or like most people will do, they'll just take the weak acid and dissociate it into its ions. We could write an equilibrium expression for this because it's a weak electrolyte and it's the same type of deal. It's products over reactants, and that's our H plus times our A minus over our HA. And that is what is referred to as a Ka value. and I'm assuming A stands for acid. So this is the acid ionization constant for a weak acid. So Ka value added to our ever-growing list of K values, Kc, Kp, Kw, Ka. We're not even halfway through, I think, but we'll have more Ks as we go through it. But Ka is for our weak acid. A Ka value that is large indicates that the weak acid strength increases with Ka value. So if the Ka value is a larger value, why does the weak acid strength increase with that? What does a large value of K mean? We mainly have what when we reach equilibrium? Yeah, we mainly have products when we reach equilibrium, which means we have a lot more free H plus in solution. So as the Ka value increases, the strength of that weak acid increases as well. It is nowhere near what a strong acid would be, but in relationship to other weak acids, as the Ka value goes up, so does the strength of that weak acid. Vice versa there, obviously, as the Ka value goes down and sort of smaller, you would have more reactants than products, so you would have a less amount of H plus in solution, which would make it a weaker acid. Any questions on that there? Now, would we expect to find a Ka value for a strong acid? Can we have a Ka value for a strong acid? The answer is no, because if it's a strong acid, it's a one-way street. Everybody, like HCl, is basically going to the product side, right? So in solution, you have 100% of these guys. There's nobody going back the other way, so you don't have an equilibrium. So that's also a very big clue that if you see a Ka value for an acid, it's a weak acid. So definitely they should only be the ones that have it. If you could find it on a Ka table, you should know it's a weak acid. So sometimes people ask, how do you know if it's sort of a weak acid, strong acid? That's a pretty big hint there, that if you see a Ka value, it's definitely weak. And if you memorize those 6 sort of strong acids, you should be in good shape of understanding which one's which. This is a table of some Ka values. Again, you have a similar table in your book. And obviously the Ka value would be provided for you in a table or something. And for some problems, you may have to look up some Ka values, obviously, to solve some of the problems. So if we wanted to calculate the pH of a weak acid, it really is a equilibrium problem because it is a weak acid. So we'll set up that equilibrium. The good news is we solve these the exact same ways we solve normal equilibrium problems, which is a nice table, and you solve it, the same way. So either you may quadratic it, may perfect square it, or you may make your assumption along the way that we talked about as well. The main difference is a lot of times we're looking for what is the pH. So we usually will get the equilibrium concentration of H plus, and then we can basically put it into our pH equation. So in addition to finding sort of the equilibrium concentrations of everybody, usually the next step after that would be to put it into just the pH equation. So why don't you give this a try here? Again, work it like a normal equilibrium problem here. Just going to use that pH equation at the end. So what is the pH of a 0.5 molar hydrofluoric acid solution? The Ka value is 6.4 times 10 to the minus 4. Or do you have a number on your paper? You have a number on your notes? No? Okay, then use that number. All right. So give it a try. Work it like a regular equilibrium problem where at the end you basically stick it into the pH equation and see what you come up with. Okay, let's take a look, see how you're doing since we're getting kind of to the end here. So a couple of things you always want to look at, especially in this class, is to make sure you don't overlook certain things that are given to you in the problem to help you understand what you should be doing. Again, as we talked about, if you look at this and you see the Ka value, that should automatically scream to you, this is a weak acid, hence the Ka part. Also should scream to you, I should do an ice table because it's really an equilibrium type problem. So again, these are things you want to think about as you go through the problems to help sort of focus you on what you should do. So clearly to do an ice table, I gotta have me a little reaction. And since this is really not reacting with anything other than going for a swim, it's going to dissociate. So that is where we want to start with, which is the reaction. And again, if you want to include the water in there, you can. You will just get H3O plus at the end. I personally are just going to show it breaking apart into H plus and F minus. Again, if you put the water on the left-hand side, you would have H3O plus and F minus as your reaction. This means that we could write our Ka expression for this, which would be the concentration of H plus and the concentration of F minus, which is our products, divided by our reactants, which is HF, and it obviously equals that number up there up on top. So because we know it's a weak acid, we got the equilibrium set up here. We're just going to really roll into our ice table like normal. Initially here, we are given that this is 0.5 molar. And just like a normal equilibrium, we have no information about anybody on the right-hand side. So it is safe to assume that those guys are going to be zeros. Also, it's safe to assume that this reaction is most likely heading to the product side because we don't have anything initially there, which means the left-hand side should be our minus x's and the right-hand side should be our plus x's like normal. So this is going to be a minus x, a plus x, and a plus x. And we're just going to carry everybody down here. So 0.5 minus x, x, and x at this point. Any questions on the ice table there? And just like a normal equilibrium problem that we've done before, the goal here is really to figure out what X is, because that is ultimately what's going to help us figure out the pH. So we're going to put our equilibrium line into our Ka expression. That will give us X times X divided by 0.5 minus X equals 6.4 times 10 to the minus 4. And that basically is x squared over 0.5 minus x equals 6.4 times 10 to the minus 4. My Ka value is a large value or a small value? It is considered small. Remember, anything less than 1 is considered small. That means I could go for my assumption here and assume that x is equal to 0 and hope for the best. So if I do that, remember, it really is in this case just this x here that we're going to get rid of. And that means that we would end up with x squared divided by 0.5 equals 6.4 times 10 to the minus 4. We're going to multiply this to the other side, and then we're going to also take the square root of it as well. And if we do that, 6.4 exponent button negative 4 times 0.5 and a little square root action on that number will give us an x value of 0.01789. We'll call it here. First off, any questions on that? We also remember that if we make the assumption here, we should do what afterwards? We should always check it to make sure that it's all good. A reminder, the way that we check our assumption is we take the x value we just got to check it. We take the x value and we divide it by what we were going to subtract it from, which is that number there in this case. And we times it by 100%. And if we do that divided by 0.5 times 100, we get something like 3.58%, which is good in this case, right? So remember, we're going with the 5% rule. So if it's less than 5%, we're all good to go. So because that's good to go, really here, we're looking for the pH, which if we go to our ice table, don't overlook your ice table, we could clearly see that we are interested in the H plus, and that equals X, which is really all that we need in this case. So we know that X equals the H plus concentration, which means our H plus concentration is 0.01789 molar. And that's really what we need to go into our pH formula. Our pH here would be minus the log of the H plus And that means minus the log of 0.01789er. And that's going to get us here a little minus the log action 0.01789. It's going to give us really a pH of 1.7, but that looks good. I'm going to say but I changed my mind there. It has one significant figure, which means we go with 1 decimal place there. And that pH is acidic, and that's good because this is an acid in this case. Yeah. Any questions along the way? Hopefully you can see the similarities here, right? Between a regular equilibrium problem and this. The only additional thing here is using the pH equation. And frankly, as I mentioned before, pretty much has to deal with all the stuff we're going to be talking about here with ice tables. You just got to do a little tweaking of something slightly different, but usually the ice table part is the same. Any questions on any of that there I can answer? Good. Yes, no? Okay. All right, we'll lay it up there for today, I guess.